Instagram was able to scale to 14 million users with only 3 engineers following 3 core principles. Keep things simple, don't reinvent the wheel, go with already proven and solid technologies. Let's dive right into it. To keep things simple, they decided to host their stateless Django servers on Amazon high CPU extra large machines. A stateless server is one that does not contain state nor session information about the client's interaction between requests. Therefore, each request from a client to the server is treated as an independent transaction. This makes scaling easier because you can spin up more boxes to accommodate high traffic. All the application servers were behind Amazon Elastic Load Balancer with 3 NGINX machines. The load balancer would automatically distribute incoming traffic evenly across the application servers so that no single server would be overloaded. Data such as users, photo metadata, and tags live on Postgres. Before Amazon RDS supported Postgres, the Instagram team had to host their Postgres servers on EC2 and attach EBS, Elastic Block Storage volumes in case an EC2 instance was stopped or terminated. EBS also offers snapshots in case data had to be restored. They decided to use PG Bouncers, which is a lightweight connection pooler for Postgres that sits between the application server and the database server. The program managed database connection pools, distribute incoming connection requests, and reduce overheads of establishing new connections to improve performance. With Postgres, each new connection took up to 1.3 MB in memory because it required OS resources to create, maintain, and close connections. This would not scale very well if you had to create a new connection for every single new request. Connection pooling helped optimize resource usage by reusing existing connection rather than creating a new one for each new request. It did this by maintaining a number of connections in cache that can be reused by future requests. This significantly reduced overhead associated with connection setup and teardown. A connection pool can be in 2 states. Idle, no, not that idle. An idle connection that is available to be used, and active connection that is currently being used. When an application requests data from Postgres, the pool manager first checks to see if the pool has any idle connections. If all connections are busy, then new connections will be created by the pool manager. If the maximum pool size has been reached and all connections are busy, then any new requests are queued until the next connections become available. As the popularity of Instagram rose, so did the size of their database. When the database gets out of control, Sharding can help manage data by splitting it into smaller manageable chunks. One of the issues that they needed to figure out before Sharding was how to assign unique identifier to each new record. This was not an issue when all the data lived in one big database, since you can just easily rely on the database auto increment ID feature. So when an ID is given, you can easily look it up in the database. However, in a sharded environment, the same ID will not tell you whether the data would live in shard 1, 2, or 3. That's why having a proper strategy is important in order to quickly determine which shard to connect for appropriate data retrieval. The ID strategy that they wanted needed to meet 3 criteria. 1, it needed to be sortable by time. 2, ideally be 64 bits to keep it small. 3, it should involve fewer moving parts as possible. They did explore a few options. The first option was to have each application server generate their own IDs using something like UUID. UUID stands for Universally Unique Identifier, which is a 128-bit number used to uniquely identify information in computer systems and applications. This approach would allow each application server to generate IDs independent of each other. The cons would be the UUID is double the expected size. 2. A dedicated server for generating Snowflake IDs by using Apache Zookeeper to coordinate nodes and generate the 64-bit unique IDs. Snowflake ID is commonly used in distributed system where the first 42 bits represents the Unix time in millisecond, 10 bits for the shard ID, and the remaining 12 bits for the sequence number. However, the downside to this approach was that it would introduce additional complexity and it would involve more moving parts. The third option was to leverage the database auto-increment IDs. Flickr employed this strategy with 2 databases where one would generate odd numbers and the other would generate even numbers. This setup is designed to avoid a single point of failure and distribute the load across the 2 database instances. They eventually chose to take inspiration from the Snowflake ID, but with a slight modification resulting in an ID structure that would be using the first 41 bits for the time in millisecond, 13 bits for the shard ID, and 10 bits for the auto-increment sequence. If the date was November 11, 2011 and this much millisecond has passed since the start of the epoch time, we convert this to binary and fill the leftmost 41 bits. Next is determining the shard ID that the data is supposed to be inserted into. If they were to shard by user ID, then the shard ID would be the user ID mod 2000 to fill the next 13 bits. Then they would take the auto-generated ID to fill out the remaining bits. They had to mod the ID by 1024 so that it would fit in the 10 bits. We then add all the binary together to form this ID, and this was the script that they used to auto-generate the IDs. And when you create a table, the ID generation is automatically attached. Now that the unique identifier was figured out, they were ready to split their massive database into logical shards. Each logical shard was a Postgres schema, not to be confused with the SQL schema. A Postgres schema is a name collection that groups database objects such as tables, views, and indexes. A database can contain one or more schemas, and each schema is isolated from each other, ensuring that objects defined within one schema do not interfere with objects in another schema. All of their Postgres instances run in a primary replica setup using streaming replication. Streaming replication is a feature in Postgres that would constantly stream changes from the primary database to the replica database in real time to ensure that replicas would always stay synchronized with the primary database at all times. Whenever Instagram needed to notify users in real time, they would push the task to Gearman, a task queue system to handle various asynchronous tasks within their application. They also had around 200 workers to consume tasks from Gearman task queue asynchronously. This offloaded time-consuming tasks such as sharing photos or notifying real-time subscribers of new updates to be run in parallel. The actual photos were hosted on Amazon S3, hosting up to 3 terabytes of photos at a time. They then used CloudFront as their CDN to help with image load time. By using CloudFront, photos would be cached closer to the user location, thus reducing latency time. Redis was used to power their main feed, activity feed, and session feed. Other technologies include Apache Sol, Memcache, Pingdom, PagerDuty, and Sentry. Covering this makes me appreciate how far technologies have come since the early 2000s. If you're just a small startup of 3 right now, you can easily spin up managed Postgres instances on AWS by yourself in a matter of minutes. That's all for this video. If you enjoyed this video, please consider subscribing to my channel for more content like this in the future. I would really appreciate it. And as always, thank you so much for watching and see you in the next one.